So day 4, unit 1, symmetry. Again, the first 3 dots, they're not wrong. I think they're just more confusing than helpful. We'll say it better later. So looking at it visually, graphically, one way to determine if it has symmetry with the y-axis, envision folding the graph on the y-axis and see if it copies onto itself. So like a parabola that's only been moved up or down. This is hard to visualize maybe for some, for others it's easy to. But if you folded the paper on the y-axis, like that would copy onto itself. So that has y-axis symmetry. I folded it over there. One way to determine if a relation has symmetry with the x-axis is fold it on the x-axis. Same thing, if you drew a sideways parabola and you folded it on the x-axis, this one's a little harder to do maybe. If it would copy onto itself, then it has symmetry with the x-axis. To determine if a relation has symmetry with the origin, this one's a little bit trickier. There's 2 ways to do it. You can reflect x and y, which is super hard to visualize. Like it's really easy to envision like one fold. Like most people's brain can fold it once and see that it copies on, either hot dog style or hamburger style, either way. But to fold twice is kind of hard to see. A better way to think of it is if you can rotate it 180 degrees and you have the same graph. It's still not super easy to do, but so if you draw a nice and neat cubic, you draw that, you hold your paper still. I'm going to rotate mine 180 degrees. Maybe. There we go. And even though my graph is now upside down, it should look the same as your graph because that has symmetry with the origin. So that one's a little bit harder to visualize, although once you get the hang of it, you start recognizing what's going on. So some examples. So y-axis, x-axis, and origin, the 3 types of symmetry. So looking at number 1A, does that have y-axis symmetry, x-axis symmetry, or origin symmetry? X-axis symmetry. And it can have more than one, so you do have to be careful. How about B? X-axis, y-axis, origin, neither, y-axis. Right, because if I fold it, it would copy onto itself. What about C? Origin. If I rotate that 180 degrees, it's helpful to have 2 graphs so you can compare. Of course, that's a little bit difficult on the test. Lean over and be like, hey, rotate yours 180 and let's see. But if you rotate that 180, it's the same. So that has symmetry with the origin. That last one tricks some people. Symmetry with the x, with the y, with the origin, or none of the above? None of the above, okay? You want to guess what some people say it has? Why? Because it's like, well, it does have symmetry. Like there is a line you could fold, but it's not the y-axis. So it has symmetry with x equals negative whatever, but it does not have y-axis symmetry. Because if you fold it on the y-axis, it wouldn't copy onto itself. All right, these are fun because these are drawing problems. Part of the graph is given. Complete the graph so that each symmetry is held. So like, here's a picture. Draw the rest of the graph so that it has y-axis symmetry. So why don't you try it before just copying what I draw? You could sort of freehand it. I'm trying to pick out a couple of key points so that it'll match up sort of well. Find some that have like integer points. integer coordinates. So something like that. And obviously I'm not, that's good enough. The intent. I'm grading the intent, not the artistry. X-axis symmetry. So I got to fold it over the x-axis. So kind of the same thing. I'm going to pick out a few key points to sort of help my graph maintain its shape here. So I'm freehanding, but not completely freehanding. I got a few key points to sort of anchor things and make sure my graph isn't too crazy. Origin, again, is kind of tricky. You got to flip it twice or rotate it, but rotating is hard to visualize. So I'm going to I'm going to flip it twice. So any point on the axis is going to stay on whatever axis it's on. And if I flip that bottom point across the x and then across the y, it ends up right there. And that green point looked like it was an integer. So again, I'm going to flip it across the x and then flip it across the y. And then play connect the dots. And so now that has symmetry with the origin. So that one's a little trickier to eyeball, at least for me. I don't know, maybe some people are more artistically gifted. It's a low bar to be more artistically gifted than I am. So maybe you can see it a little easier. Questions on that? You've seen that before. X-axis symmetry, y-axis symmetry, rotation symmetry. All right, that's the visual of it. Now, if you're given the equation, then it's a little bit harder. To determine if a relation has symmetry with respect to the x-axis, replace x with negative x. And see if you get the same thing. So y-axis is replace x with negative x, see if you get the same thing. Makes sense then that the x-axis would be replace y with negative y, and see if you get the same thing. And then the origin is replace x with negative x and y with negative y. You gotta do both. And then the fun part, not so fun part, is that because it could be any of those three, you have to check all three when it asks. You don't get to just or you have to show all three. Even if you can tell by looking at it, and after you've done a few, you'll be able to tell by looking. Even if and when you reach that point, you still have to show the work. You can't just look at that and be like, yeah, I know what's going to happen. It's X or Y or origin. You got to show the work. So, number one, determine if it has these symmetries. So, we'll go in the order that it was listed up there. So, y-axis symmetry, negative x goes in for x, and we see if we get the same thing. So, 2y squared, negative 1 over, and then we replace x with negative x. Plus 3. Sometimes the answer is obvious and sometimes not. Is this the same thing as our original? No, because that x is now negative, and there was nothing to sort of fix it. So that's a no. Not the same, therefore not y-axis symmetry. All right, x-axis symmetry. Negative y goes in for y. So in place of y goes negative y. Everything else stays the same. Is that the same as the original? Why, yes. Yeah, when you square the negative, it becomes positive. So that is a yes. Yes, it does have x-axis symmetry. And then we'll check the origin, which is both substitutions, negative x in for x, negative y in for y. And sometimes the two negatives cancel each other out and it sort of works out. Like, even though it feels like, well, I really messed up that equation, depending on where they are, they work it out. Sometimes yes, sometimes no. This time, is this a yes or a no? That's a no. Like, that one gets fixed, but then you're still stuck with that negative, so that one's a no. Dylan, did you have a question? All right, let's do the same thing for this example. And again, even when you get to the point, and you will get there, and most of you will get there, that you can look at it and know if it's going to be, which one is going to work, because things start happening like the squareds. But I still need to see the work so that you've shown how you know that it works or doesn't work. Y-axis. Just looking at it, we'll see if you're there already. If I plug in negative x for x, am I going to get the same thing? No. Why not? There's an x squared. Yeah, but there's another x, right? So one of them's fixed, but the other one, no. So I need to at least see the substitution, so I know that you know what the test is. After that, if you can tell by looking it works or doesn't work, that's fine. X-axis, negative y in for y. Leave my x alone. And then put negative y in for y. That's an easy one, I think. What do we think on that one? That's a no. That's not the same thing. The origin, we're going to make both swaps. Negative x in for x. Man, negatives all over the place on that one. Yes. Right, because the squared fixes this negative, and then the two negatives make a positive. So that one turns out to be a yes. It does have symmetry with the origin. Do you? Yes, it is possible that there would be no symmetry. You could get no for all of them. You could get yes for all of them. Like, just think of a picture. Think of a graph that has all the symmetry. What's a graph that has all the symmetry? Not y equals x. Circle. It's not a very well-centered circle. Like x squared plus y squared equals 9. And because everything's squared, it fixes all the negatives, so it has all the symmetries. There's also weird combinations of things that can and can't happen. Maybe you'll figure those out along the way. Maybe not. Doesn't really matter. But like, one of them is, if it is both x and y, then it's definitely origin. You still have to show it. If it is x or y, only one of them, then it's definitely no on the origin. You don't have to know that. You guys show the work anyway. But there are like some built-in sort of, not shortcuts, things to think about as you're working them. All right, even and odd function. An even function is when for each x in the domain, f of negative x equals f of x. Which is another way to say, if you plug in negative x for x and you get the same thing. So even function is the same as y-axis symmetry. So that's probably the easiest way to say it. Even is the same thing as y-axis symmetry. Odd is the same thing as origin symmetry. The O's go together, O, odd, O, origin. And actually, let's do the examples first, then we'll talk about the shortcut. Determine if each is even, odd, or neither. So when it asks for even, odd, or neither, it's really asking the same questions we just did. Does it have y-axis symmetry? Does it have origin symmetry? So you don't have to memorize anything new for even and odd. You just have to attach even to x-axis and odd to origin. So it's not more tests. It's just a new name for the same test. It's just different names for symmetries. And so I'm just going to change that to y. And so let's check. Well, I can tell right away what will work and what won't, but let's check y-axis. So that means change the x's. Is this one going to work or not? Can you tell? No, it's not. Why not? Those powers are still negative. Yeah, those odd powers make it negative. So you can write it out if you want, or you can stop there and say, no, that's not going to work. So therefore, it is not even. Odd is the same as origin. So that means change the y's and the x's. Negatives all over the place again on this one. Ooh, what do we think about that one? I'm going to show one more step here. Negative y equals negative x to the fifth plus 4x cubed. Is that the same as the original? Yeah, if you divide by -1, you make it the same. So yes, it does have origin symmetry, which means it's odd. Now look at the power on that, or the powers on those x's, and see if you can figure out why it's called even and odd. If all the powers are odd, then it's going to be odd. If all the powers are even, it's going to be even. If you got a mix, then it's neither. And if you got something that's not even or odds, like fractions, like, yeah, you better just work through the process. So even and odd is a nice shortcut by calling it that, but well, it's going to work here. Let's see. Even is y-axis is negative x in for x. 2/3. What in the world do I do with the 2/3? What's the 2/3 mean? What's the top number and the bottom number do? Do you remember this? Top number is the power, bottom number is the root. I don't know how far in our department it's infiltrated, but we used to have a teacher here who used to say the flower power grows on top and the root grows underneath. So it's kind of silly, but it helps you remember which one's which. So the power's on top, the root grows underneath. So if I take the cube root of a negative number, I get a negative number. And if I square a negative number, I get a positive number. So this turns out to be the same thing. So be careful, don't go backwards. You can't be like, therefore 2/3 is an even number. It doesn't work that way.
I pledge allegiance
to the flag
of the United States of America
and to the republic for which it stands, one nation, under God,
indivisible, with liberty and justice for all.
And now to the Texas pledge. Honor the Texas flag. I pledge allegiance.
Number 3 is not a function, so you're kind of just done. So that's a trick question, but be careful. What's that? Right, so the circle is neither an even or odd function either, but it does have x-axis symmetry and y-axis symmetry and origin symmetry.
So if it's talking about even or odd,
That has to be a function. So this one has x-axis symmetry and y-axis symmetry and origin symmetry, but it's not a function, so you can't say it's even or odd. So it's kind of tricky.